Let's continue. We are currently discussing the topic of anomalies, in other words, symmetry breakings by quantum effects, where you have a classical symmetry of the Lagrangian, which, however, is not respected by the quantum theory, and that can happen in the path integral if the measure is not invariant, or in dimensional regularization if you cannot extend the action to a d-dimensional action which is still invariant under the original symmetry. And the example that we started with is scale invariance, which is typically broken by almost every quantum field theory. And the simple reason is that whenever you have divergences, ultraviolet divergences, you need to impose some regularization, renormalization procedure, and any such regularization, renormalization procedure introduces some dimension full scale. Dimensional regularization does it in the sense of this mu square parameter in front of d-dimensional integrals, but any other regularization also imposes some dimension full scale. For example, a cut-off scale at which you cut off the ultraviolet integrals, or a lattice of space-time where you have a lattice spacing which is dimension full. So whatever you do, scale invariance is practically always broken, and instead of the simple classical scale invariance relation, you have something different, which is called Callan-Semantic equation, which is the equation that we wrote down in the morning. Now we come to the second example, which is very well known, and actually in many presentations it is the first example which is discussed. In my opinion, it is more complicated to discuss, therefore we do it second, and that is the anomaly of chiral symmetry connected to chiral fermions which are left-handed or right-handed, where you have either left-handed or right-handed projection operators in the interactions, or the gamma 5 matrix in the interactions. So let's discuss that. And actually both anomalies are discussed also on the exercise sheet, which I now distribute. So this is the second example. Chiral fermions and the corresponding anomaly of chiral symmetry. So this is connected to the gamma 5 matrix in the gamma algebra. And let us consider here simply a massless QED theory to get a simple example. And this has a Lagrangian L is equal to psi bar I d slash psi plus E times Q times psi bar A slash psi plus the usual other terms. And so here you have a kinetic term for a massless fermion and an interaction term of that fermion with the photon field. Just ordinary QED, and actually this Lagrangian has two symmetries. It is not only gauge invariant under the usual local gauge transformations corresponding to QED, but it has an additional symmetry. So let me write down, it has two symmetries which are global symmetries. One of them is the ordinary QED gauge transformation, which you can do in a local form even, but of course also globally. So you would do a phase transformation of the spinor psi going into e to the I alpha times psi. That leaves the Lagrangian invariant. If alpha is x independent, then the derivative doesn't do anything, and you do not need any transformation of the photon field. The Lagrangian is just invariant. But actually, you can do it independently for the left-handed spinor with alpha left, and independently also for the right-handed spinor with alpha right, because all these terms in the Lagrangian, they simply decompose into sums of terms for the left-handed spinor only plus terms for the right-handed spinor only. Therefore, you can do independent phase transformations for both spinors. That is equivalent to saying that psi goes to e to the I alpha times psi, which is the ordinary transformation, and the second transformation, let's say, e to the I gamma 5 times alpha 5, say, times psi. So you have one transformation where the whole C-node transforms with the phase, or where the left and right-handed components transform with opposite phases. So these are two different ways to split up the two independent symmetries. But the Lagrangian is invariant under both symmetries. And so then in QED, this one can be done even in local form, where alpha becomes x-dependent. That one is only valid in global form, where alpha 5 is x-independent. But anyway, you have two global symmetries. And as you know, global symmetries are enough to get a conserved Noether current. So therefore, the theory has two conserved Noether currents, classically. So let's say the electromagnetic current dmu j mu equals 0, and the second one dmu j a mu equals 0, where this j a mu is the Noether current to the corresponding to the gamma 5 transformation. And so let me write down just this one. The current could be written as I times psi bar gamma mu gamma 5 times psi. This is the so-called axial current. So, and now the point is that on the quantum level, you cannot arrange that both currents remain conserved. At most, one of them can be conserved also on the quantum level. To a certain extent, you can choose which one remains conserved. In QED, we must choose that the current which couples to the photon must be conserved, because otherwise the gauge theory interpretation becomes inconsistent. And then that means in this context, the conservation for the axial current gets lost on the quantum level because of quantum effects. So this chiral symmetry is broken by effects. In QED, the mu j mu equals 0 must hold because of gauge theory interpretation. So that was the discussion that we had, for example, in quantum field theory 1, where we needed a conserved current coupling to the photon. Otherwise, this interpretation with Gupta-Bloiler negative norm states and so on becomes inconsistent. And then the outcome is that d mu j a mu becomes non-zero at the loop level. And the details are your exercise. Your exercise is exactly that. Calculate for precisely this theory a conservation law corresponding to the axial current. You will have to do a one-loop calculation, and in momentum space you will get an amplitude with a Lorentz index mu corresponding to the axial current, and you can contract with a momentum which flows into that vertex. In momentum space, the derivative becomes a momentum, and if that conservation law would be valid on the quantum level, the contraction with a momentum would have to give 0, but you will calculate that it's actually non-zero, and that is the anomaly. So I will not go through the technical details now. Let me give you some physics. Calculate for precisely this theory a conservation law corresponding to the axial current. You will have to do a one-loop calculation, and in momentum space you will get an amplitude with a Lorentz index mu corresponding to the axial current, and you can contract with a momentum which flows into that vertex. in momentum space the derivative becomes a momentum, and if that conservation law would be valid on the quantum level, the contraction with a momentum would have to give 0, but you will calculate that it's actually non-zero, and that is the anomaly. So I will not go through the technical details now. Let me give you some physics overview. You can distinguish in general two cases for such an axial anomaly. Let's say case A is you have a true anomaly of this kind. Where a global symmetry is broken. And this indeed happens and is relevant for pion decay. So precisely this calculation is actually relevant for pion decay. So there, let's say pion decays, the neutral pion is the one in question, decays into gamma gamma, and the corresponding amplitude for this decay can be visualized like this. So a pion is like a bound state of two quarks, let's say up quark and anti-up quark. I draw the lines next to each other to denote that it is a bound state. Then the two quarks split and generate a fermion loop, a quark loop in this case, and you get two photons out of the vertex. And so then pion decay is mediated by this Feynman diagram. On the theory level, it corresponds to the calculation that you will do in your exercise. It corresponds to a matrix element of here the axial current, Ja mu, and here a matrix element of two electromagnetic currents. Because the pion is a pseudo-scalar particle, so it couples with gamma 5, and therefore this coupling here can be described by a vertex which looks like the axial current vertex, whereas those couplings are ordinary Feynman rules from QED. Therefore, the interaction Lagrangian contains the ordinary electromagnetic current. So in terms of such currents, one needs a matrix element which looks like this. And if there were no anomaly, the contraction of this with a pion momentum would have to give 0. And the result is the contraction is not 0. And therefore, you get a large, let's say, numerical result from this Feynman diagram, giving rise to a fast decay of the pion into two photons. And looking at the details, the calculation reproduces exactly the measured pion lifetime. And on the other hand, Ja mu, and here a matrix element of two electromagnetic currents. Because the pion is a pseudo-scalar particle, so it couples with gamma 5, and therefore this coupling here can be described by a vertex which looks like the axial current vertex, whereas those couplings are ordinary Feynman rules from QED. Therefore, the interaction Lagrangian contains the ordinary electromagnetic current. So in terms of such currents, one needs a matrix element which looks like this. And if there were no anomaly, the contraction of this with a pion momentum would have to give 0. And the result is the contraction is not 0. And therefore, you get a large, let's say, numerical result from this Feynman diagram, giving rise to a fast decay of the pion into two photons. And looking at the details, the calculation reproduces exactly the measured pion lifetime. And on the other hand, prior to that, people noticed that there was a contradiction between this argument and the measured pion decay before they knew there was such an anomaly. There was a, let's say, discrepancy.
أعتقد أن هذه الآلية لها علاقة بالوارد ايدنتيتي. كما ذكرت أن الوارد ايدنتيتي يمكن أن تكسر إذا كان هناك unphysical state. هذا unphysical state عبارة عن combinations بين physical و unphysical state أخرى، وهذا ما يعطي طاقة عالية في وسط التفاعل، مما يفعل الفضاء ثنائي الأبعاد آلية للدفاع النفسي. أعتقد أنه هنا يتأثر بهذا. طبعا الكتل هي التي تتأثر بالكسر للأيدنتيتي، بحيث أنه تظهر كتل مختلفة. أعتقد أنه هنا البايون هو الذي يتأثر بهذه الأيدنتيتي أو كسر الأيدنتيتي، وهذا ما يؤدي إلى تحلل البايون، وبسبب الكومبينيشنز للطاقة والطاقة الزائدة في المكان. هذه الطاقة الزائدة في المكان يؤدي إلى كسرها وتوزيعها بسرعة شديدة. هذه السرعة تؤثر على البايون ذات نفسه. إذا البايون بسبب هذا التيار الذي يسمى الأكسيال كارنت يكون عالي في اتجاه وليس عالي في اتجاه مثلا، هذا ما يؤدي إلى تحلل البايون، بحيث أنه الكونتراكشن بواسطة المومنتوم لا يعطينا زيرو كما ذكر. طبعا هذه وارد ايدنتيتي ولا يعطينا زيرو، يعني هنالك حصل كومبينيشنز بين هذه الطاقة، وبالتالي في الامبليتيود أعطتنا نتائج في هذا المحور بالذات، الأكسي في هذا الأكسيال بالذات. فهي تتعلق، أعتقد أنها تتعلق بالنون سيمتري بالنسبة للأنفيزيكال ستيت، بحيث أنه الأنفيزيكال تكون مثلا أكبر من الفيزيكال، وهي عبارة عن كومبينيشنز. هذه الكومبينيشنز أدت إلى ضغط الفضاء ثنائي الأبعاد أكثر فأكثر، فيما أعطى كسر الكتل وتحمل ذلك البايون فاينوت. أعتقد ذلك.
You can see between this sort of way of looking at pions and the measured outcome. So the anomaly is actually very important, and in this way you can see you measure directly the effect of the anomaly for chiral symmetry. So
طبعا هذا بالإضافة لأنه الكايرال سيمتري إنه الفضاء ثنائي الأبعاد يتأثر بسبين معين ولا يتأثر بسبين آخر. يعني مثلا إذا كان السبين متقارب مع بعض البعض، يعني متشابه السبين، فإن ذلك يولد مجال مغناطيسي يقوي بعضه البعض. وإذا كان السبين في اتجاه واحد، فإن ذلك مجال مغناطيسي يقوي بعضه البعض، هنا يحصل انتراكشن. أما إذا كان السبين في اتجاهين مختلفين، فإن ذلك يجعل المجال المغناطيسي يعاكس بعضها البعض، وبالتالي هذه الجسيمات لا تتفاعل مع بعضها البعض. هذا ربما يدخل في هذا الموضوع، يمكن العلماء يبحثوا في ذلك.
Actually, one can write it. That is also an answer to a question in the morning. There is a true relationship which is valid on the quantum level. The exercise is not quite enough to prove this equation directly or completely, but it gives an indication that something like that can be true. So the true relationship is that this is proportional to the following: epsilon mu rho sigma times 2 field strength tensors corresponding to the photon field. And the prefactor here is of course of one loop order. And therefore at the classical level you have zero, but at the quantum level you have something non-zero which describes everything. So this is a very important and well-known physical effect. So anomalies exist, they are predicted, and their predictions agree with measurements. And that is the case if you have a global symmetry which is hit by such an anomaly. Let us now look at the opposite, or let's say second possible case, namely local symmetries. let us suppose there is an anomaly of local symmetry. In other words, a local symmetry is a gauge invariance. Gauge invariance is not really a symmetry. Gauge invariance means that there is a redundancy in the theory description variables of your theory, which you can use to gauge away unphysical degrees of freedom and to make manifest the physics content of your theory. If there is anomaly in this gauge invariance, then the theory just becomes inconsistent because the interpretation of physical versus unphysical degrees of freedom breaks down. And remember, we needed in the previous lectures gauge invariance to separate physical degrees of freedom in the Hilbert space with positive norm from unphysical degrees of freedom with negative norm states. The S matrix should be unitary and the probability to produce negative norm states should be exactly 0 and so on. And if there is an anomaly in gauge invariance, then this in the theory description variables of your theory, which you can use to gauge away unphysical degrees of freedom and to make manifest the physics content of your theory. If there is an anomaly in this gauge invariance, then the theory just becomes inconsistent because the interpretation of physical versus unphysical degrees of freedom breaks down. And remember, we needed in the previous lectures gauge invariance to separate physical degrees of freedom in the Hilbert space with positive norm from unphysical degrees of freedom with negative norm states. The S matrix should be unitary and the probability to produce negative norm states should be exactly 0 and so on. And if there is an anomaly in gauge invariance, then this would not hold anymore. Therefore, the theory would become inconsistent in the sense that we cannot interpret it as a physical quantum theory. Therefore, for local gauge invariance, there must not be an anomaly. It is not allowed that a gauge invariance has an anomaly. Otherwise, okay, and therefore let us now spend a moment on sketching what is the condition for the absence of such anomalies. So what I am doing now is really only a sketch. At this point you cannot see why what I will do is sufficient, but from the exercise you will certainly see that it is necessary to do what I will do. Because the exercise will show what are the Feynman diagrams which produce the anomaly. Those are Feynman diagrams with such triangular fermion loops. So what we should require for the absence of anomalies is that such triangular fermion loops vanish. If they vanish, then there cannot be an anomaly coming from them. And in some other ways, we should prove that there cannot be an anomaly from anything else. And so let us now write down the condition for those triangular loops. And to be specific, I use now a different Lagrangian because here that was adapted to the case where the axial current is not connected to gauge invariance. Let us now write down a theory where the anomaly could be related to gauge invariance. And that is a theory where we have only left-handed fermions, psi bar L I times I capital P slash psi L I. That means that we have a gauge theory with covariant derivative and gauge bosons, and all the gauge bosons couple to some set of left-handed fermions, psi L I. And there might be many of them. All of them couple in some sense to the gauge bosons, and inside of this there is a term with a generator matrix TA times vector bosons A mu A. And then the generators would tell us how each fermion couples to each gauge boson. Then the relevant Feynman diagrams are these ones, where we have three external gauge bosons. Let's say here with index, gauge group index A and Lorentz index mu. Here with gauge group index B, Lorentz index mu. Gauge group index C and Lorentz index rho. And there are actually precisely two such Feynman diagrams, namely ones where the fermion arrow is in this direction, and the second one where the arrow is reversed. That essentially also means the same thing as flipping the indices B and C. So, and in calculating those Feynman diagrams, the only thing that really matters is not the loop integral, because that is always the same. What differs between the different gauge theories is the generators here. And so the only thing that we need to take care of is how do the generators, in other words, the structure of the gauge group and representation, how does it enter the calculation? And so here you get a trace at each vertex. You have such a generator here, TA, TB, TC. So, it's a loop, so therefore you get a trace of the product of three such generators. And here you get the trace TA, TB, TC. And here you get the reverse order TA, TC, TB. And this is added, and therefore in total the whole thing is proportional to the trace of this TA times the entry commutator of TB times TC. Okay? So it's exactly a sum of two terms. This is the trace. And this trace depends on the one hand on the gauge group in general, but then for each gauge group specifically on what representation of the fermions do you choose. And that trace should be zero. This is the condition for vanishing of the anomalies, because if it vanishes, then no matter what the loop integrals do and so on, the Feynman diagram will be zero, and then there will be no anomaly. So let's put this to zero and simply say, so this box here, let's put it here. This is the condition for vanishing chiral gauge anomaly. Every gauge theory must satisfy this. There is no exception to this. And every gauge theory with fermions can be brought into that form, because if you have a gauge theory which would contain right-handed fermions, then you can write the right-handed fermions as charge conjugation of left-handed fermions. Therefore, every fermion, right-handed, left-handed, whatever, can be brought into the form of only left-handed fermions. And therefore, even for QED or QCD or whatever you want, you can bring the Lagrangian into this form. And then, of course, if you convert a right-handed fermion into a left-handed anti-fermion, the generators might have to be adapted, but in the end you can see what are the generators for only the left-handed fermions. They must be put into the formula, and the formula must give zero. And this is the case for all the gauge theories that you know. For QED it is the case simply because if you do that for QED, the left-handed fermions and the right-handed anti-fermions, they have opposite charges. Therefore, for every term, there is an additional term with exactly the negative sign. Therefore, for QED, automatically it adds up to zero. And the same is also true for QCD, where you have left and right-handed fermions acting in the same way. But for the standard model, it is highly non-trivial, and you can check it that it works also in the standard model. Yeah. Well, yeah, I mean, this is basically the outcome of your exercise, that those give rise to the anomaly, so it is not something that I can fully explain now. In other words, this is the explicit calculation. However, as I mentioned briefly, one thing that one has to make sure is what is in total the, let's say, range of possible breakings of symmetries. Of course, I can tell you that these diagrams vanish, but then you might ask, okay, but what about other Feynman diagrams? Maybe they contribute also to some anomalies. And that is a different study, and I will give you some information on that study in the next section. But clearly, these diagrams could give rise to an anomaly, and they vanish under this condition. And so let me stress again, there is the notion of vector-like gauge theories. They couple only two full spinors, psi equal psi left plus psi right, if like QED or QCD. If you have that, then for each left-handed fermion, there is a right-handed fermion with the same charge. If you convert a right-handed fermion into a left-handed anti-fermion, then it has the opposite charge, and therefore there is automatically zero here because each term has a negative counterpart. So these are automatically anomaly-free. But there are chiral gauge theories where obviously that is not true. Here the condition is non-trivial. We can check it, for example, for fun, maybe just for the hypercharge or electric charge sector of the electroweak standard model. Electroweak standard model. Let's say hypercharges. So this is true for any combination of generators. So in this case, it would mean that we require that the trace of hypercharge cube in the standard model should be zero, where the trace means now a sum over all left-handed fermions of the standard model. And so, do you want to check it? I think yes, we should check that. So what, maybe it's also a topic for the other lecture, but let's do it here. So what are actually the hypercharges in the standard model? What are the left-handed fermions of one generation in the standard model? We have on the one hand the left-handed quark doublet, which consists of the left-handed up quark and the left-handed down quark, and this comes in three colors. We have the left-handed lepton doublet, we have the right-handed quark singlet, but that should now be converted into a left-handed particle. So we should look at this object. You are charge conjugated because that is actually a left-handed fermion field, and that comes also in three colors. The same for the right-handed down quark and the same for the right-handed electron field. Now, what are the hypercharges? Hypercharge of this is 1/6. It's always the average of the electric charges. So 1/6. Here we have minus 1/2. Here we have in principle 2/3, but charge conjugated, so minus 2/3. Here plus 1/3, and here plus 1. Now we need to add up a hypercharged cube. Hypercharged cube, and we need to do a trace over all fermions. That means, for example, from here we get 1 over 216, but times 3 because there are 3 colors, and times 2 because there is up and down. Then here plus this cube gives minus 1 over 8 times 2 because there are neutrino and electrons, and here we get minus whatever 8 over 27 times 3 colors, and here plus 1 over 27 times 3 colors, and here simply plus 1, as simple as that. And now you add it all up, and looking at it, you obviously get 0. That's like the magic of the anomaly cancellation of the standard model. And you see that the anomaly cancellation only works if you allow in the standard model both quarks and leptons, and you need precisely the 3 colors of quarks in order to make the anomaly cancellation happen. That is very interesting and intriguing. So the standard model with only leptons looks perfect, but actually it is an inconsistent ill theory because it violates gauge invariance at the loop level. Similarly, a standard model for only quarks is also inconsistent. And if you would replace QCD with 4 colors instead of 3, the electroweak sector would automatically also become inconsistent. So that is quite striking.
أعتقد أيضا الموضوع له علاقة بالمجال المغناطيسي. يمكن البحث في هذا الأمر، خصوصا الليفت هاندد والرايت هاندد. هذه لها علاقة بالمجال المغناطيسي وقوة المجال المغناطيسي عند الأبعاد الصغيرة. يمكنكم البحث في هذا الموضوع.
Okay, any questions to this? Then otherwise we go to the next topic. Good. So small physics remark on the standard model. And so if you want to go away from the standard model and look at physics beyond, then this is something that you also have to keep in mind. For example, if you change the fermion sector in the standard model and you want to add, postulate some additional fermions, then you have to worry whether you still fulfill this anomaly cancellation condition. So you have to watch out about that. And similarly, if you have a different gauge group, then you again have to think about the anomaly cancellation for that gauge group too. Good. And there is always the legend of the PhD student who was working for 3 years on a theory, and then in the PhD exam some other guy said, okay, but your theory has an anomaly, and then the whole theory is for the rubbish bin, and you can stop the exam. So therefore, take this into account. Okay, next topic is the so-called West-Zunino consistency condition. Conditions. So let us now assume what I would call a generic renormalization framework. This is often also called so-called algebraic renormalization. By this I mean that we go away or generalize from dimensional regularization and just look at any regularization renormalization framework which is in agreement with a basic requirements of any such framework which makes the theory finite but at the same time is consistent with fundamental properties like causality and unitarity in quantum field theory. So, for example, that could be dimensional regularization after removing the 1 over epsilon poles and taking the limit d going to 4. So that would be one such framework, but we do not use that, but we generalize from it. If you do that, then you automatically get a finite theory which is consistent with all fundamental properties, but you do not know whether it's correctly renormalized, because at this stage you are still allowed to add finite counter terms which might be necessary in order to restore symmetries which were broken before, as we discussed in this context. And just for simplicity, we now assume linear symmetry transformations. And then I want to show you how you can in principle obtain the most general anomaly that there can be in your theory. So we now assume that our symmetry transformation is delta phi, which is linear, and let us, to be definite, write it in the form of some Lie group transformation. So this is a Lie group generator. That would, of course, the typical case. Since it is a Lie group generator, we have commutational relations. TATB is equal to some structure constant FABC times TC. Then we define Watt identity. We already saw how the Watt identity looks like, which was this linearized invariance relation of the effective action gamma, which looks identically to the invariance relation of the classical action. But we write it in the sense of an operator equation, so we introduce a Watt operator that I call capital WA, which is defined such that capital WA is a differential operator, integral over x of the variation of the field TA ij phi j times derivative with respect to phi I, always at x, and to make it nicer, let's put a minus sign in front of it. So this is a Watt operator, and why do I call this Watt operator? Because now the Watt identity that we wrote down before is simply WA acting on gamma is equal to 0. Because the identity was precisely this integral over the field transformation times the functional derivative of the effective action gives 0. Now, but we do, now let us assume that at the order h bar to the n minus 1, so at some previous order, the Watt identity holds.
شفتوا هذا ما يأكد كلامي. أنا في معادلة الوارد ايدنتيتي، المعادلة ذاتها فيها الإفكتيف أكشن، وذكرت أن الإفكتيف أكشن يمكن لا يكون يساوي 0 لأنه فاي أصلا تتغير، وتغير فاي يعطي تغير الإفكتيف أكشن، وبالتالي معادلة وارد ذاتها في نفسها الايدنتيتي اللي هو الوارد ايدنتيتي هو في نفسه يمكن يعطينا لا يعطينا 0، هو في نفسه يمكن لا يعطينا 0، وبالتالي ضربه في أي امبليتيود ولا أي شيء لا يعطينا 0. فالأمر يعتمد على التغيرات التي تحصل في وسط التفاعل.
So this equation is valid. for all generators A. And then we go to the next order. So at the order h bar to the n, we assume that the Watt identity may be broken. Then we would have at this particular order an equation WA on gamma is not zero, but it is something, let's call it delta n, with index A, so the breaking depends on the Lie group generator A that we use to do the transformation, and for every A there might be a different result, and I put an index n for n loop order. So this is really an expression which is zero before n loop level, and at the n loop level it may be non-zero. Then there are a few things that we know about this capital delta n, the possible breaking of the Watt identity. Namely, it is from general renormalization theory. The breaking can at most be related to the ultraviolet divergences of the theory, and therefore from the necessity to do regularization and renormalization procedure. And from those we know that they are always local. Divergences are local in the sense that they can be written like a Lagrangian or like an action with local products of fields and derivatives. And the same is true for such a delta. So renormalization theory tells us that this delta A is a local product or expression, and similarly to the divergences, it can contain only dimension at most 4 terms if the theory was renormalizable to begin with. Otherwise the dimensionality would be bounded by something else. So this is what we know. And then we can now look at the Lie group structure of the whole thing. Because the generators satisfy a Lie algebra relationship, and the Watt identity is expressed by Watt operators which contain the generators, there is the commutation relation also for those operators. Commutator of WA with WB gives in general I times FABC times WC. So automatically if you commute them, then all the derivatives drop out, and what remains is the commutator between the generators, and so this replicates the commutation relation of the generators. And so if you combine this with the possible breaking, then now you can act with another W onto this equation. And then you can study what happens if I act with a commutator onto gamma. Then on the left hand side you get a commutator of 2 W's acting on gamma, which is 1 W acting on gamma, and on the other side you get 1 W acting on the delta. And therefore you obtain the following relationship: WA times 1 breaking B minus the opposite WB times the other breaking A is equal to I times FABC times the breaking with index C. And there you have your consistency condition on your possible breakings. So the possible breakings must be local expressions in the fields and derivatives which have this relationship with the original Watt operator. So they are constrained by the symmetry operation. And okay, let's first stress this. So these are the West-Zumino consistency conditions. And the practical outcome of this is that now, if you ask the question that you asked before, what is, or you implicitly asked it, what is the most general anomaly that can possibly appear? The most general anomaly that can possibly appear is the most general solution to this equation. what is the nature of this equation? The nature of this equation is that you have here something which is local. So this expression, you can think of it like a Lagrangian. So you can make the most general ansatz for a Lagrangian, and it is constrained by that equation. So you solve. So this is a purely classical expression. It has nothing to do with quantum operators, green functions, Feynman diagrams. It is a tree-level-like expression or classical expression. And you can figure out the most general solution in terms of some deltas which solve that equation. And once you have the most general solution, you know which anomalies there can possibly be. And maybe this equation has no solution at all, then you know immediately there cannot be an anomaly. Maybe the equation has precisely one non-trivial solution, then you know maybe there can be one anomaly. And if you calculate that explicitly and it is 0, then you know you are done, and so on. So now you can find the most general solution, and this gives the most general possible anomaly. Then there are some cases like maybe all possible anomalies can be cancelled by adding counterterms. In which case we would actually not call them anomalies, but just spurious breakings of the symmetry. Or maybe there are few non-trivial solutions. So this depends on the case, but this Wess-Zumino consistency condition is the tool which allows you in complete generality and for all orders at once to answer the question whether your theory can in principle have an anomaly and how many different anomalies there can be. So let me stress this again, just to say it twice. You can solve this equation once and the solution doesn't depend on the loop order n, because at any loop order that could be a classical-like expression. Therefore, you have an all-order result. So that is very powerful. And I will not work out any particular examples now, because that would be a different thing, but I just want to use this lesson today to show you some structures and how things can be used and how they are connected. So I hope this is okay. Actually, I thought about it a little bit. So today's lecture does really not contain too many full derivations where you can understand them from beginning to finishing. Instead, I will drop a few results and sketch the derivations. And my excuse is that it would take really long and be extremely technical to do the full derivations of all those results. And on the other hand, I think it's more important to have an overview of the methods and what are the possible outcomes of those methods, and then you can fill in the details that are maybe relevant for your work whenever it's applicable. But it would be a pity to spend a lot of time on one aspect and then not mention all the others. Therefore, that is what we will do. So here I've told you a method. The method is clearly defined and clearly derived, but applications are left for the reader. Now let us do something else. Do you have any questions? Let us do something else. which is a further application of the West-Domino consistency conditions, but for a different context. Here we assumed a global symmetry and a linear symmetry. These are the West-Domino consistency conditions, and so this is just to show you the structure. And that might be something that could be applied to the axial symmetry relevant for chiral decay, because that was exactly such a global symmetry, which was not gauged, but which was global and which was of course also linear. So that would fit here exactly. Now the very important other case are gauge theories where we have BRST invariance, a much more complicated symmetry, which must hold in the final renormalized theory, otherwise the theory becomes inconsistent. That is nonlinear and local, and it must not be broken by anomalies. And so previously I gave you a sketch of the renormalizability proof for Yang-Mills theories, and in that sketch, if you remember maybe, I told you that we assume that a regularization like dimensional regularization automatically preserves the symmetries, such that we did not worry about anomalies, possible symmetry breakings, because that was just an assumption. And then I sketched the rest, which is still non-trivial. But now let me fill in exactly this detail. What happens if we do not know whether the symmetry actually is valid on the regularized renormalized level, as it can be in the standard model where we have gamma 5 and axial and chiral transformations. So this is an additional detail to the sketch of the renormalizability of Yang-Mills theories. So one might call it part 1, whereas what we did so far was part 2. So the section where we did this was section 264. There we had an assumption that the Slavnov-Taylor identity describing BRST invariance holds manifestly at all steps. Now we assume that this might not be the case. We assume that it is valid in an iterative sense. We do renormalization order by order, and up to some point we have managed to achieve that the Slavnov-Taylor identity is valid at the order h bar to the power n minus 1, but may be broken at the next order. So at order h bar to the n we might have a breaking, and let us use now the notation of the Slavnov-Taylor identity I introduced in the morning. So we integrate over x, and then we have the product d gamma by d ki of x times d gamma by d phi I of x. And the ki was a source for the BRST transformation. So what we have here is the expectation value of the BRST transformation in the presence of sources k, multiplying the derivative of gamma with respect to phi. That was this modified by quantum effects formulation of the symmetry of gamma. And so now at the previous order that would be 0, but now at the next order we assume that it might be broken by some quantity delta n. That is now our starting point, and similarly to here, we want to discuss what are the properties of this possible breaking delta n and whether we can actually make it vanish. So what we know again is that this is local as before because of renormalization theory, and in a renormalizable theory the operators which appear here are dimension 4 or less. And let me also give one or two comments on this. So in the morning we derived this, but if you remember the fine print was that in the morning the Slavnov-Taylor identity was only valid at k equals 0, because k was just artificially introduced on top after deriving the Slavnov-Taylor identity, unless the k part of the action is still invariant under the symmetry, and that is the case here. So that corresponds to, in the path integral, that we have e to the I times Lagrangian plus these k sources times the BRST transformation of all the fields plus the normal j sources times all the fields. And because the BRST transformations are nilpotent, s square equals 0, the k parts here of the Lagrangian are actually also BRST invariant. And that means that this Slavnov-Taylor identity, according to our derivation from the morning, is valid for all k, not just at k equals 0. So here the BRST transformation of this k part is 0 because of the nilpotency. Therefore, the above can be valid for all ki. Now another note on the case. The case are the sources for BRST transformations, and the BRST operator small s is fermionic. So the BRST transformation of anything has always the opposite statistics to the original quantity. And so therefore, in order to make the whole expression here bosonic, which is must be as the exponent of the path integral, the case must have the same statistics as the BRST transformation of a field, and so the case has the opposite statistics as the original field. So Ki has the same statistics, fermionic or bosonic, as Sii, and therefore the opposite statistics as the original fields Phi. Then let us derive consistency conditions. And in order to do that, let me introduce, sorry for that, yet another notation, which is, however, very nice, I think at least, star notation, A star B.
طيب هناك شروط للكي فيلد حتى تكون لاجرانج انفاريانس، أو تحت الشروط تكون فيها السلافنوف ايدنتال انفاريانس، أنه تكون الكي statistical opposite. وهذا يظهر في الكوارك أنتي كوارك. الكوارك أنتي كوارك يجلسان معا في وضع جميل وتمام وليس هناك مشكلة. ولاحظت إلى أن الكوارك أنتي كوارك هما الاثنين statistical opposite. فشرط أساسي لهذا أن يكون الكوارك أن تكون أنتي الشيء والمضاد. لماذا ذلك؟ لماذا؟ أيضا يعود الأمر للإسبين على ما أعتقد. يمكن العلماء يبحث في هذا الأمر، يعود الأمر إلى الإسبين شرطا من أجل أن تمكث الجسيمات دون أن تتفاعل، أن يكون الإسبين لها مختلفا وليس واحدا، بحيث أن يلغي بعضها البعض. أو المجال المغناطيسي، لأن المجال المغناطيسي قوي جدا عند تلك الأبعاد، يجب أن تكون المجال المغناطيسي متنافران. إذا تنافر المجالان المغناطيسيان هذا يؤدي تقارب هذه الجسيمات يخلق قوة تباعدية. طيب أما تباعد هذه الجسيمات فهذا يعني أن الفضاء ثنائي الأبعاد سيكون مرتاحا. لا، هو ليس مرتاحا. لماذا؟ لأن الكوارك ذات نفسه ثقيل، عند أبعاده حرة هو ثقيل. فالفضاء ثنائي الأبعاد يجب أن يجد آلية أن يحكمه مع بعض البعض بطريقة أو بأخرى. يعني مثلا إذا تباعد المجال المغناطيسي ينقلب لأحد الكواركين ويصبح تجاذبيا. يعني السبين ينقلب لأحد الكواركين ويصبح تجاذبيا، أو الشحنة. فهذا الانقلاب يجعل نفس القوة التي مؤثرة على التقارب تكون مؤثرة على التباعد، لكن هنا القوة لا تصل لما لا نهاية. أو في هذا الكوارك تصل لأنه كوارك يخرج معه بالفور، يخرج معه أنتي كوارك بالفور، يخرج معه عن طريق الجاذبية. طبعا لا يوجد جسيمات تخرج من العدم، إنما الجسيمات تخرج بفعل طاقة موجودة في المنطقة، وهي طاقة الجاذبية أو طاقة الكهرومغناطيسية. فهنا الطاقة موجودة ولا التناظر مكسور، فإذا كوارك يخلق معه كوارك آخر مباشرة، لا غضاضة في ذلك. إذا الخواص المغناطيسية يمكن تفسر لنا هذا الموضوع أيضا.
Is an abbreviation for that. Similarly, before we introduce these Watt operators in order to write the Watt identity, now we introduce such a star symbol, which is the following. It's just this with A and B. Symmetrized, A and B are treated in the same way. So once where A derivative with K, B derivative with respect to phi, does the opposite. Okay, and then the Slavnov-Taylor identity would be simply gamma star gamma equals 0 in this new notation. So that is what the notation can be used for. But in this notation we can write down some other relationship, namely for any object A we have automatically the following: A star A star A, 3 A's give 0. So why is that? So independently of whether there is a Slavnov-Taylor identity or not, here you have lots of combinations of derivatives with respect to k and phi. And k has the opposite statistics from phi. And simply because of that, this automatically adds up to 0. And let us just look at maybe one single term out of the many terms that you can get. So A star A will contain a term A with k times A with k derivative. Then we hit on it with another A star. Then that means we get A derivative with respect to k times the derivative of the whole thing with respect to phi. That generates, for example, a term where you get two derivatives of A with respect to phi I, phi j, times one derivative A with respect to ki, another derivative with respect to kj. So one term would be, let's say this, dA phi I, phi j times dA ki. Okay, terms like this. And then you see, if this is bosonic, then that is symmetric in Ij, and this is then automatically antisymmetric in Ij. If this is fermionic, it's the opposite. But in any case, this adds up to 0. And so you can go through all the terms. They automatically add up to 0. So this is in a way a trivial identity. There is no physics inside of it. It is just a mathematical identity because of the structure of derivatives having to do with the opposite statistics of phi and k. But that allows us now to derive a consistency condition on the possible breaking, because if I hit this with another gamma star, then I get gamma star times delta is 0 automatically. And that is a consistency condition. So we get gamma star delta n must be 0, but actually we are only caring about the order h bar which we are now considering, because we are in our iterative renormalization at this order. So let's throw away all higher orders than this. This starts at order h bar. Therefore, if we want h bar to the n, if we only want h bar to the n, we need from here only the h bar to the 0 term, in other words, the classical limit. So the only thing that is relevant for us is the classical action star the possible breaking, and that will be 0. So and that is our consistency condition. So all the possible breakings are local expressions of dimension 4 or less, which satisfy classical action star delta equals 0. And that is again a purely classical, purely algebraic equation which constrains the possible appearing breakings. So again, therefore, we have the task of finding the most general solution. And once we know what the most general solution is, we can discuss the answer to your question. And in this case, if you go through the algebra, and we will not do that, but if you just solve this classical equation, then you will find that there are solutions to it which correspond to spurious breakings which are actually trivial and which can be compensated by just changing a little bit the counter terms of your theory, and then afterwards the symmetry holds. But there is precisely one and only one non-trivial solution to this which cannot be compensated by any possible counter term, and that is the one corresponding to the triangle graphs. So this only non-trivial solution corresponds to the chiral anomaly and is given by these triangle graphs which are proportional to the trace of this combination of generators TA and T-commutator TB-TC. And then if this anomaly absence condition is fulfilled such that you choose a specific fermion representation for your gauge theory such that the combination of generators vanishes, like we did in the standard model, then you know that this only non-trivial anomaly doesn't exist. Therefore, there is no anomaly at all in your gauge theory. So you can, whatever the breaking is, add some counter terms, then the breaking is cancelled. Then there is no breaking anymore at this order h bar to the n, and then you proceed as we did in the previous section, where we assumed that the Slavnov-Taylor identity holds at all steps of the calculation. So let's just say if there is no anomaly, we can assume delta n equals 0, and then we proceed as in section 216. Okay, so this is how you can control the possible breakings of symmetry in a theory, and this is one ingredient in the full rigorous proofs of renormalizability of gauge theories. In particular, you need that for the electroweak standard model. Yeah. The box means now gamma star gamma equal delta, and then we hit on this box with another gamma. We use this, so then we have manifestly zero, therefore gamma annihilates delta, and then we expand in orders of h bar. Let me add a historical comment. The first time it was done like this, and where this entire approach was used and clearly spelled out, was in the paper by BRS on BRS invariants. So they invented basically this approach. So also to set it a little bit into current context, this approach is not so urgently necessary if you have dimensional regularization, and you know that dimensional regularization automatically preserves the symmetries, like in QCD and QED, such that the Slavnov-Taylor identity really obviously holds at all steps of the calculation. Then obviously there are no anomalies, and obviously you don't need to solve anything here because there is nothing to do. However, in the electroweak standard model, because of that issue of chiral symmetry, it is not like this. The Slavnov-Taylor identity is not manifestly valid, as you will see in the exercise. And then this discussion makes sense and is a relevant ingredient. And also maybe you know that here we currently have some research projects exactly in this direction. Therefore it's also worth mentioning it.
طبعا كل هذه التناظرات المكسورة لا تظهر للعين، إنما تظهر في وجود الكتل. يعني الكتل بسبب أنها تعمل على إعادة التناظر، وتكون التناظرات المكسورة داخلها. لهذا نحن ربما في التجارب لا ننظر هذه التناظرات المكسورة، لكن ننظر إلى كتل مختلفة وننظر إلى كتل متنوعة. هذا ما يعبر عن التناظر المكسور، لأن الكتلة عموما تحاول أن تجعل الفضاء متناظرا، وهي تحمل في داخلها عدم التناظر هذا. وبذلك إذا أردنا أن نختبر عدم التناظر في كل هذه الايدنتيتيز، ما علينا إلا أن نشوف التنوع في الكتل، خصوصا الكتل التي تكون الفرق بين كميات تكون كبيرا. يعني مثلا ميون ونيوترينو فرق كبير في الكتلة، الإلكترون والنيوترينو فرق أقل في الكتلة. هذا ينتج من ماذا؟ ينتج من نوع التفاعل، وينتج من كثرة هذه الايدنتيتيز كلها.
Good. Any other questions? We will stay at the topic and do a little bit more in this direction. So the same gamma star notation will still be relevant, and this equation with the delta. So equations of that structure remain relevant. But I want to go back to the sketch of renormalizability that we discussed at the time in our section 2. So now we have sketched how we can make sure that there are no anomalies and how we can make sure that indeed the Slavnov-Taylor identity holds as it should. And then I said we can now proceed as we did in section 2. But what did we actually do in section 2? It was a very rough sketch. We said if the Slavnov-Taylor identity holds, then all divergences can be cancelled by counter terms coming from our renormalization transformation. G goes to G plus delta G, phi goes to square root of Z times phi, and so on. But what do you actually need to do in order to establish that? So let me also give you a little bit more details on this part of the proof. So this is more details on part 2 of the same proof. So as in section 264, we now assume that the Slavnov-Taylor identity is valid. Then the question is, what is the most general structure of divergences? And therefore, what is the most general structure of the required counter terms which are needed to cancel the divergences? And the outcome of that investigation should hopefully be the required counter terms are the ones that we have introduced. So, how can this be established? We go to some specific order in our iterative procedure, let's say h bar to the n. Now we know that the Slavnov-Taylor identity holds because we assume it, and here we have shown how we can establish that it can be done. But there may still be divergences. That means we have gamma up to the n loop level. Let's say I write gamma smaller or equal to n stands for the effective action we normalized up to the n loop level such that the Slavnov-Taylor identity holds, but divergences might still be there. So I can write this as gamma smaller than n from previous iterations in the procedure, then gamma at the order n finite parts plus gamma at the order n divergent parts. So all the previous orders are already finite, and the order we are now considering, there are still divergences, and our job is now to figure out what are the order n divergences. And to make it simpler, let us combine these smaller or equal to n finite plus n loop divergences. So this is the structure of our effective action, and we said the Slavnov-Taylor identity holds already at this level, so that means using the star notation that is 0. Now, how can we obtain information on the divergences from this equation? Well, the divergences are part of that equation, so in this equation, including the divergences, we get 0. Therefore, we can exhibit just the divergent part from this equation by really plugging in for gamma the sum of the finite plus the divergent parts, and then we have individually the 0 for the finite parts and individually 0 for the divergent parts. And then we have an equation for the divergences. So maybe let's simply say this whole left-hand side actually is the following: finite star finite plus 2 times finite star divergent plus divergent star divergent. Now, the only order in perturbation theory that we care about is order n loop level. So we can look at the equation, which is sorted according to orders in perturbation theory, strictly at the order n loop. And then at this particular order, what do we see? We see that n loop times n loop is 2n loop, which is bigger than n loop. We assume n is bigger than 0. So that is too high order, therefore divergent times divergent can be neglected. Here we have strictly n loop times anything below it. If we only want the strict order n loop term from this is exactly n loop. It means here we need exactly only the classical limit. And from here we get the order n loop part. So we have gamma all over equal than n finite star gamma equal or smaller than n finite plus and from here we only need order h bar to the n plus 2 times gamma classical limit times gamma n loop divergences is 0. And now we have first of all separated the orders, and also we have separated divergent and finite contributions. This is definitely finite. The only divergent contributions come from here. The sum of the two is 0. There cannot be a cancellation between divergences and finite expressions. Therefore, it must be individually finite, and so it means we have a consistency condition for the possible divergences. And as you see, it is exactly the same consistency condition as the one for the possible anomalies. And so here, this is again a known quantity. So this is a known classical expression. And about the divergences, we of course know from renormalization theory, they are also local expressions. And if the theory is renormalizable in the power counting sense, then they are constrained by dimensionality at most 4 or less. Exactly the same kind of thing as for the delta. And so again, we can solve this equation in generality. It's just a purely algebraic, purely classical discussion. And the most general solution of this will give us the most general structure of possible divergences which can appear at any order in perturbation theory.
طبعا الدايفرجنت يحصل في دايمنشن يكون أقل من 4. هذا يتفق مع نظريتي في شيء. أنا الفضاء ثنائي الأبعاد هو ثنائي الأبعاد ليس رباعي الأبعاد، وأن الصراع يكون في هذه الدايمنشن الثالث والرابع. يعني إذا خرج الفضاء رباعي الأبعاد كاملة، يعني هذا سيطر الكتلة كاملة، وهذا ما نراه في الواقع في واقعنا هذا 4 أبعاد. نحن الآن نتعامل ب4 أبعاد، أما في وسط التفاعل يكون هناك صراع بين الفضاء ثنائي الأبعاد وبين هذان البعدان الآخران الذي يخرج من الفضاء رباعي الأبعاد ثنائي الأبعاد، أو يخرج من الكتلة ذات نفسها أو الطاقة ذات نفسها. فنجد أن هذا الفضاء في هذا التفاعل، هذا عدم الانسجام هو الذي يولد اختلاف الكتل وكثرة التناظر.
Okay. And so that is already a little bit more details than what I told you the last time. Now you know a structure, how you can obtain the most general form of the divergences. And so by solving this, you can compare with the ansatz that we did by using this renormalization transformation, and you would find that the most general solution corresponds to those structures. We can, if we have time, go a little bit in additional details. Namely, how does such a general solution look like? You would do a general ansatz. We know that our divergences at the n loop level should be equal to minus your n loop counter term action, which would be equal to minus an integral over some n loop counter term Lagrangian, which would lead to local Feynman rules which can cancel the local divergences which can possibly appear. And then what we need to do is to make a most general ansatz for any local counter term Lagrangian, and to solve the most general counter term Lagrangian which solves this equation. So this would be a local Lagrangian, which can in principle depend on all the fields in our theory. But we know a few things. Again, we know it is constrained by dimensionality. But we also know some other things depending on the details, but we will typically assume that global gauge invariance holds manifestly, because there is essentially not much room for breakings of global gauge invariance. That is a linear symmetry which can be more manifestly valid than the local symmetries on the Lagrangian level. So we can assume this as well. And then you can do a general ansatz, for example. One ansatz could look like this. The counter term Lagrangian, it's easiest to incorporate into the Lagrangian also these sources k. They also need counter terms. And then you start with a field with the highest dimensionality. And the field with the highest dimensionality is the k source for the Faddeev-Popov ghost. Very unphysical object, but this object here has dimension 4. Because the Faddeev-Popov ghost has dimension 0, and the product of the two must have dimension 4. So this is a source with dimension 4. Therefore, it must be multiplied in the Lagrangian with something which cannot depend on any other case. It must be multiplied with something of dimension 0. What must it be multiplied with? Dimension equal to 0. And ghost number, what must be the ghost number of whatever is the coefficient of this k? It must be the same ghost number as the BRST transformation of the Faddeev-Popov ghost, which is ghost number 2. How can you get something which has ghost number 2 and dimension 0? In our theory, practically all objects that we know have dimension bigger than 0. Only the Faddeev-Popov ghost has dimension exactly 0. So what you need here is exactly a product of two Faddeev-Popov ghost fields and nothing else. So we immediately know that. And then the only solution is to write down something like FABC times CBCC. That is the only thing that you can possibly write down with some coefficient. So you already know the most general ansatz from here. Then you can go on, for example, you have k for the gauge field, again with some coefficient, and you think about it. What you must have here is dimension 1. It must have one Lorentz index. It must have ghost number 1. So the only two terms that you can possibly write here are derivative of one Faddeev-Popov ghost field, or product of one gauge field and one Faddeev-Popov ghost field with two different coefficients, and so on. So you can do this for all the sources k, and then you have something extra, a counter-term Lagrangian without any sources, which depends on all the fields. And then you know already quite a lot, and you have not even used the consistency condition. And if you now add this information to the consistency condition, then you can derive a lot of relationships between all the coefficients here. So you see here one coefficient, here two coefficients, some more coefficients, and all the coefficients will be correlated by that consistency condition, and this correlation will tell you that the renormalization transformation that we showed is exactly the one that you need in order to cancel all divergences. So dot 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 a few steps, and then you see the solution is the one of section 264. As a reference for where you can find the dot dot dots, this is done in a few textbooks. For example, it's done in Weinberg's textbook, section 17.2 or so, and it's also done in the Denner textbook, and it's also done in the Kubo textbook, in all cases in nice ways. All right, I think that is all I wanted to tell you today. Now you have an overview about some methods using the effective action gamma, how you can deal with gamma in order to understand and control, in particular, control symmetries at higher orders. And the next time we will go to a more physical topic, namely spontaneous symmetry breaking, and discuss what happens in that case. Very good. In the last 2 minutes, maybe I can tell you a little bit about the exercise to get you going. The exercise is maybe a little bit technical, and it's not something for 5 minutes, I think. So exercise 1 is something for 5 minutes, because I basically want you to go through the derivation of the Kellen-Symanzik equation that we did in the lecture in the morning. And all the details that you need, you can find either in other textbooks or, for example, in the video that I linked and that I mentioned in the morning. But I mean, it's not only in the video, it's in many, many textbooks. You can find exactly this, and then by watching it, you can immediately derive the equation that we have in the morning, so that you have a complete picture of that. But let me discuss this. Your second exercise is to compute these triangle diagrams and to really see that there is such an anomaly in the case where you have the following situation. You have here an axial current. So here you have a coupling gamma mu times gamma 5, and here you have only gamma mu, and here you have only gamma rho. So here you have two QED vertices, and here you have one axial current vertex. And then there are two Feynman diagrams, this one with the arrow in this direction and the other one with the arrow in the opposite direction, and you need to add up the two, and the sum will then have this anomaly. And between the two, there are a lot of cancellations. And you should do the calculation in this Toft-Feldman-Breitenloher-Meison scheme of dimensional regularization, because the big problem comes from the treatment of gamma 5. And there are some details on the exercise sheet, but the basic point is that all quantities you can now think of, first of all, in d dimensions, like momenta, gamma matrices, derivatives maybe, or polarization vectors epsilon. They are in principle all d-dimensional, but for each you can do a split, and the notation that we can use is this one. So the split is d-dimensional goes into 4-dimensional plus d minus 4-dimensional parts. So that is 4-dimensional, and that is d minus 4-dimensional, and you can do that for all quantities. For example, gamma mu is gamma bar mu plus gamma hat mu, and so on. And then for some quantities, like the external polarization vectors, epsilon is equal to epsilon bar mu, because that is a polarization vector of a physical photon, so there is no epsilon hat that is 0 in this case. And the same is true for the momenta of the external particles in the Feynman diagram. So this momentum here is 4-dimensional, it is physical, so it has no d-dimensional component. But the loop momentum, that is d-dimensional, and the gamma matrices at the vertices in the loop, they are also d-dimensional. And so for them, you can distinguish between the 4-dimensional and the d-dimensional parts. And then you can do some calculations involving gamma 5. So for example, if you have gamma 5 times gamma mu, then this is not the same as minus gamma mu times gamma 5 like it normally would be in 4 dimensions, but this is only true for the 4-dimensional part of the gamma matrices, whereas for the d-dimensional parts, for epsilon dimensional, you get a plus. That is the definition of gamma 5 in d dimensions, and that is the reason why these symmetries do not hold if you extend the Lagrangian to d dimensions, because only the 4-dimensional part behaves in the symmetric way, whereas the epsilon dimensional part behaves in an unsymmetric way. So this is the core of the problem. This is where the symmetry breaking comes from. And so now you have to do the calculation using this formalism. And the exercise is hopefully simplified as much as possible. For example, by using those polarization vectors for the external photons here, we always contract immediately with those polarization vectors, which means that whenever here at this Lorentz index rho there appears something with a hat, it immediately can be dropped, because it will be contracted with the epsilon, which has no epsilon dimensional part. So generally speaking, as it is also written on the exercise sheet, if you have something like this, k bar mu times k hat mu, that is 0, or k hat mu times epsilon bar mu, that is 0, because they live in different orthogonal spaces. Or let's say k mu dot p mu, if you split them, then this is k bar mu times p bar mu plus k hat mu times p hat mu, something like this. Okay, so this is the technical building blocks that you need in the calculation, and apart from that, your job is to basically simplify as much as possible the expression up to the point where you can see that contracting this with the external momentum doesn't give 0. In principle, it is okay for you to stop at this point. You do not have to calculate fully what it is, as long as you can show me or anybody else that the result is non-zero. That is okay, that is good enough. Then you have proven that there is such a momentum. Okay, so yeah. Do you know what to do? Otherwise we could write down, maybe you need to go, but we could write down here the numerator of this whole thing. So, okay, maybe let me do it. So this single Feynman diagram, it would be a loop integral over some loop momentum k, and then we have to specify here there is the momentum q, k plus q, and here maybe k1, k plus q minus k1, and here k, and so on, and then your expression is minus the trace, because you have a fermion loop, and the three propagators are here I k slash divided by k square from this propagator, then I times gamma rho from this vertex times I k slash minus q slash minus k1 slash divided by this same thing square times I times gamma nu, then times this propagator k slash plus q slash divided by k plus q square from this propagator, and then finally times I gamma mu gamma 5. So this would be the trace. And so what you need to do is to evaluate the trace, and in evaluating the trace you can hopefully use quite a lot those formulas that I gave you. So it's a trace with up to 6 gamma matrices. Maybe by adding the two Feynman diagrams first and simplifying, you can reduce the trace to a trace of 4 gamma matrices before actually evaluating the trace, but you can also blindly just evaluate the trace as it is, and then you get thousands of terms and add them all up. It's not thousands. It's pretty okay. I mean, it takes maybe a few hours to do the calculation, but on the other hand, you learn something really fundamental, namely the existence of those anomalies is of course one of the hallmarks of quantum field theory. Where really quantum field theory does something qualitatively distinct from all the non-field theory quantum theories. Only because of the infinite number of degrees of freedom coming from the fields, you get the necessity for regularization and the divergences and also the anomalies. And of course, feel free to search in the literature. I mean, this is not a new calculation, so it has been done. The first person who calculated this anomaly in the context of pion decay was an experimentalist. So that should motivate you to at least also be able to do this. So I think the legend is that this experimentalist didn't know so much about quantum field theory, so he simply sat down and calculated the bloody thing, whereas the theorists in his department maybe said, there is no point in calculating, we know that there is this Watt identity, and because of this we immediately know what the result is, and he calculated and got something different, and he was right. Because they didn't know about the possibility of such anomalies.